Um, I should probably begin by thanking the organizers for giving me this opportunity to speak here, and thank you all for coming. So I'd like to tell you about some work that I've been doing for the past few months with Loga, trying to understand this question of scattering against black hole horizons. So this is a broad outline of my talk. I'll begin with what my question is, and I'll sort of try to describe what my question is and sort of motivate my question. And then I'll sort of suppress all of the technical detail and tell you what we find and what our salient features and results are, and then summarize and conclude with some future work. So almost the first thing that any of us learns about a black hole is that anything that you throw into a black hole gets sucked into it. That's like the classical intuition that almost any of us learns. But then quantum mechanically, since Hawking's calculation in the 70s, we know that a black hole also radiates. It actually radiates at some temperature, which is given, which I've sort of which I've sort of indicated in this equation 1 here. You can see that it's some very small temperature because there's some h bar on top, and m here is the mass of the black hole. So the statement is that quantum mechanically, the black hole also radiates like a black body at this temperature. So then naturally the question arises that if you throw something into a black hole, if I throw this into a black hole, it can hit the radiation coming out of the black hole, this thermal radiation coming out of the black hole, and then rebound. So we want to understand such scattering processes. So the question we're asking is, how do we think about processes where particles scatter off of the Hawking radiation coming out of a black hole? So this is of course believed to be a very small effect because Hawking radiation itself is like a very small effect. So that's really the question I'm asking. And to motivate the question a bit, an astrophysical motivation would be like if you have a pulsar orbiting a black hole and this pulsar is sort of emitting electromagnetic radiation, how prominent is the effect of this electromagnetic radiation hitting the black hole and then sort of rebounding back? How much of this radiation would you see? And apart from this astrophysical motivation, there is of course a more quantum gravity motivated motivation, which is to say black holes are like laboratories or test beds for you to try to understand quantum features of gravity. So then this becomes a question of asking like trying to understand features of quantum gravity using such a black hole. And then since 3 of the speakers spoke about ADS-CFT, an ADS-CFT sort of motivation would be to try to understand strongly coupled plasmas in which the elements of the plasma are interacting very strongly. How do you understand the behavior of such plasmas? So that's the kind of question we'll be answering if you sort of believe in ADS-CFT. So that's kind of the question, and this question is sort of a very difficult question, as you can imagine, because it's a very non-equilibrium sort of system. You have some black hole which is radiating at some temperature, and then you're trying to ask, you're throwing something in, what are the scattering, and it's some finite temperature non-equilibrium sort of process. And it's more so difficult if the difficulty is compounded if you're trying to understand it for a real black hole out there in the sky, because a real black hole out there in the sky is a spherical black hole, and like spherical geometries, as most of us know, is much more difficult to try to understand than a planar geometry, because in a planar geometry you can do plane waves. In spherical geometry you have to do spherical harmonics and vector spherical harmonics and so on. So we want to try to understand the most basic and characteristic features of this problem. We want to understand the qualitative features of this problem by considering a toy example, a toy model, and such a toy model is provided to us by this planar black hole, or also called a black brain, in an asymptotically ADS spacetime. So what I mean is that in ADS, which is to say in a negative cosmological constant, you have a solution to the Einstein equations which has just a planar horizon. So the horizon is just a plane, and anything that passes that plane doesn't come out. So something like that, some statement like that. So that's sort of the question, and I'll sort of jump in to tell you what we find now. What we find is basically that you can sort of understand the black hole as a bath. Like in a very open system, open quantum system point of view, what you can say is that what I mean by an open system is that consider a ball falling through air, and then if you want to sort of try to describe the ball, you wouldn't try to understand the air surrounding it. You would sort of integrate out the air and say it's a minus gamma v, and gamma has all of the information contained in this air interacting with this ball. So what we find is that a similar statement exists for this black hole. You can sort of treat the black hole as a bath, and you can sort of treat all the particles outside this black hole as an open system, and you can integrate out the bath. And another more interesting statement that we find is that you can focus only on the exterior of the black hole. You can completely forget about the interior of the black hole, and you can do all your calculations in the exterior of the black hole. And how do we do these calculations? So what we find is in doing these calculations, what we find is that the natural description or the natural way to think about such processes is that there are two kinds of particles in the exterior. So say you're throwing some pion in. Why pion? Because it's a scalar particle and it's very simple. So if you're throwing some pion in, then what we are seeing is that there is a Hawking pion in the exterior, which is like a Hawking fluctuation coming out of the black hole. And then there are pions you can throw in and are coming out, which are called the external particles. So I will denote these Hawking particles by some capacitors and external particles by some diodes. You'll see why, because if you sort of describe it by diodes and capacitors, only diagrams that contribute are the diagrams in which there is some current flow. It's some intuitive sort of way to draw these diagrams. So one physical process that can happen in such a setting is you sort of throwing a pion in, and then two pions are coming out of the black hole. That such a scattering process is possible. And one such diagram that contributes to such a scattering process is what I've shown here. So the dotted line above is like the boundary of the spacetime. It's like the boundary of the ADS. Many of the speakers showed you cylinder for an ADS. So the boundary of the cylinder is like the boundary of ADS. And the horizon is basically the horizon of the black hole. So what you're saying is that one particle is going in, which is the first hand you see there. One pion is going in, and there are two pions coming out. And there is some non-trivial Hawking fluctuation happening near the horizon or outside the horizon. So that's one example of a physical process, and then you can imagine that there will be many more diagrams like this, and there are actually hundreds and hundreds more physical processes that happen like this, which all we calculated, and it was a lot of fun. So some other examples are what I've given here. You can see that in the second diagram, for example, what you're saying is you're throwing two pions in and two pions are coming out, and they've interacted with no Hawking physics of the black hole. This is just some, for those of you who are familiar with quantum field theory, this is just some Feynman diagram. That's the usual Feynman diagram, which has not changed in any way. The only change in all of these diagrams I'm drawing is that we have two different kinds of propagators. So what we studied is diagrams like these, where three particles are interacting at one point, which is like a phi cube theory, and that second order and third order in perturbation theory. Which is what I mean by two such points and three such points, bullet points in the spacetime. And the main result of what I want you guys to take from this talk today is that all of these diagrams and all of these diagrammatics that I've developed, and this statement that you can work only in the exterior, the diagrammatics that comes out is exactly the diagrammatics for an open field theory, which I'll come to in a minute. So we have derived the set of rules, and to compute the contribution for each of these physical processes, like we have a consistent set of rules, and these set of rules satisfy many consistency conditions. Well, a few consistency conditions, two of which I've sort of described here. One of which is if you throw something in and just let it be, it should equilibrate. Right, in a Brownian sort of process, if you put a Brownian particle in water, it should equilibrate eventually. That's like the statement of a fluctuation dissipation theorem. The dynamics does not break the equilibrium. So that fluctuation dissipation theorem, here it will be called the KMS relation, is satisfied. That's a non-trivial check that we have checked for all these physical processes, and the probability for all processes happening must add to unity. That's sort of like a unitarity statement, which we have also checked in such processes. But the point I was talking about, the point that I want you guys to take home is that we see that the black hole can be thought of as a bath and can be integrated out. But more than that, what we see is that these are this diagrammatics that we have developed for this calculation is exactly the diagrammatics for a cubic open theory, for a general cubic open theory. So the statement we have is that if you put something in a black hole spacetime, and if you want to try to understand the field theory in that black hole spacetime, you can just completely forget about the black hole and sort of write down rules without the black hole. And from an ADS CFT point of view, this open field theory for these scattering processes in this black hole spacetime will correspond to an open field theory, can be mapped to an open field theory to try to understand scalar probes in strongly coupled plasma. So say if you have a quark gluon plasma, and if you have a scalar particle buzzing through this plasma, how do you understand an open field theory for this scalar particle? It will be the same open field theory. And so this is a summary that I've been trying to tell you. The black hole acts like a bath and makes the field theory open. And this field theory has some neat diagrammatics of external and Hawking particles, equivalently diodes and capacitors, which allows to calculate all of the correlators of the field. Well, not exactly all of the correlators. A kind of correlators that we would like to calculate are the out of time order correlators, which many of us may be familiar with in the context of quantum chaos, for example. So such correlators we would like to calculate, and this is ongoing work. I'm currently working on including those correlators. And then there is, of course, the question of trying to generalize this formalism for other fields like gauge fields for electromagnetism. If you throw photons into the black hole, how does the black hole sort of behave? Does this open effective field theory still, is there still a statement of an open EFT in such a case? We believe that there is, but the calculation needs to be done. And another interesting question that you can probably ask is, what happens if you make the space-time itself dynamical? Here I've sort of considered a black hole and then thrown things at it, but what if the black hole is sort of evaporating or something? What happens when you make the space-time dynamical? What happens when you have gravitational waves in the space-time? So for that, you can see Loga's talk tomorrow, and that's where I'll end. Thank you for your attention. I'll be happy to take questions.
Thank you, Godwin. Now it's the time for questions.
Can I ask a question?
Yes, surely.
Yeah, so the question is, suppose instead of a black hole, you had just a thermal object, say a star, but at the same temperature as the black hole. Mm-hmm. And you do scattering outside the black hole outside that object as you did. Right? Mm-hmm. I mean, is it, are you saying that by doing a scattering involving a few particles, you can actually distinguish the black hole from a normal thermal object at the same temperature?
I did not make that statement, but so you're asking if I can distinguish between a thermal object and a black hole by doing such a scattering experiment?
Yes, exactly.
I do not know. I don't think I can comment on that.
Okay. Thank you.
Hello? Yes. Yeah, just a small question. So since you get an open field theory here, why do you say that the probability have to add to 1? It's not unitary in general, right?
Well, if you sort of consider the full system, the full evolution is of course unitary.
Okay, but I thought the point was to not do that.
Yeah, sure, but in this full system, that there has to be a unitarity constraint, and that unitarity constraint is satisfied.
Okay, great.
And this OpenEFT comes out of that. So this OpenEFT sort of is obeying that constraint.
Okay, and just another small question. So why did you say that the fluctuation dissipation theorem is the same thing as the KMS relation? Can you explain this? Or?
Can we talk about that later?
Yeah, okay, sure, no problem.
Okay, yeah, sorry, Godwin, in those diagrams you had, why did you say the diagrams with current in them would contribute, and why not any arbitrary diagram?
Okay, that's basically what is coming out of our calculation. The calculation basically tells us that all of the influence of the black hole can be written down in some neat integrals, like some Feynman integrals, or some Witten diagrams that look like this. And the Witten diagrams have this natural interpretation that only diagrams in which there is some current flow will contribute. But more precisely, maybe I should say that these arrows tell you the time flow in these diagrams. So diagrams in which there is no time flow won't contribute. That's probably an answer. Thank you.
So I had a very general type of question. What kind of scenarios do you envisage where your kind of work, where you throw particles towards a black hole and get stuff out, could actually help detecting Hawking radiation?
I haven't seriously thought about this question, so I don't think I should comment on it. Yeah.
Okay, thanks.
Any more questions?
Same question as Ashok. But I thought you're incorporating somewhere that it's a black hole, right? Yes. So you should be able to distinguish between a black hole and a normal star from your scattering
Yeah.
Results.
Okay. That's true. But I mean, that I think is true because all of our calculations are done in some space-time. So what we're saying is that the interior of the black hole can be forgotten, and the rest of the space-time can be kept, and you don't need to worry about the Hawking physics of the black hole, and you can do some normal QFT in the exterior of the black hole.
Okay.
So it's a non-trivial space-time statement. I mean, I'm not saying you can sort of do this in flat space. You can do this here. I'm not saying you can integrate out the black hole in the sense that you can do the same sort of scattering processes here with some non-trivial QFT. That's not what I'm saying.
But see, a black hole and a star will have the same space-time geometry outside, right? So if you are not actually probing the horizon, then as far as the classical space-time is concerned, there is no difference between a black hole and a normal star.
Right.
So where exactly are you using the fact that it's a black hole in a non-trivial way, that these are Hawking radiation and not a radiation from a star?
Well, we're using the using the horizon physics. Okay, so I haven't explained any technical calculation to you, but I think we're using the fact that there is a black hole because we need an event horizon to do this calculation. We need a horizon. We need the horizon of the black hole to do this calculation. I don't think without the horizon you can do this calculation.
So you think that if it was a normal star, you will get a different answer?
I think so. Yeah. I should probably have said this earlier. Yeah.
Okay. Okay. Thank you.
Let us all thank Godwin again.